So in this session at GroupBy, David Fowler is going to be talking about writing your own encryption routines in SQL Server and then breaking them, co-hosted with Daniel Hutmacher, who'll be asking the questions on here. So take it away, David.
Thank you very much. And thank you very much for having me here at GroupBy. It's pretty cool to be here, pretty cool to be talking. So for the next hour or so, we're going to have a little bit of fun with encryption. We're going to pop the hood. We're going to get down and dirty with the cogs and the pulleys of encryption. Have a little look about how it works underneath. We're going to have a little look about how we can incorporate, how we can implement into T-SQL, and also going to look at any vulnerabilities, attack vectors, and how we can look at cracking those routines. So that's a good start. My little clicky thing's not working because it's not switched on. That's it. Things work better when they're switched on, don't they? If that's the biggest goof of the day, I'll be happy. So a little bit about me. My name's David Fowler. I've been working as a SQL Server DBA for around 15 years now. I've had a few spells in development. I've worked as I worked in embedded systems written in C. I've worked in web apps written in .NET, but SQL's my love. SQL's my passion. That's my drive. That's what I love to do. I blog over at SQLundercover.com. Myself, colleague Adrian Buckman. We have Chris Jones as well, just recently joined us. Just if we find anything a little bit cool, a little bit interesting, we'll chuck a blog post up there. Also any scripts that we find a little bit interesting, we think people might find useful, tend to go up there as well. So feel free, to go up there and have a little poke around. When I'm not nerding over databases, I'm a keen triathlete, I'm a keen cyclist, I love racing, I love bikes. I race road bikes, mountain bikes, cyclocross, time trial, pretty much anything that's got two wheels, I'm going to be all over it. If you want to get in touch, you can drop me a line at david@sqlunder.com. I'm also on social media. I'm on LinkedIn. I'm on Facebook. I'm not on Twitter as myself, but SQL Undercover has got a Twitter account. So again, if you pop over to SQLundercover.com, you'll find the links to all of our social media on there. So feel free to get in touch with me how you like. So the agenda for the next hour. We're going to start off with a little section that I've called the arcane sciences. So this is just a few fundamentals that we're going to need to know, we're going to need to get our heads around before we can start looking at encryption itself. We then got our first algorithm, our first cipher, which is the XOR cipher. We're going to have a look at the Caesar cipher. We've got something that I've called the Caesar XOR collaboration, a little section called Pimp My Cipher, and we're going to finally finish up with what I've called shifting the key. So before we do get started, there is a little bit of a disclaimer. Basically, all the encryption routines in this presentation are purely for demonstration purposes only. So that means that myself, SQL Undercover, or anyone else I may be associated with cannot be held liable for any damage that may be arising from using them. So basically, if you take any of these algorithms, use them in production, someone comes in, nicks all your top secret data, you have been warned, don't come crying to me. So that brings us on to the first section, the arcane sciences. So what are the arcane sciences? What is this ancient knowledge that was known to the scholars of yore way, way back when and long, long forgotten by the modern DBAs? We're talking about a couple of things. We're talking about binary and we're talking about bitwise logic. Now we need to get our head around these things because a lot of encryption algorithms work at a binary level. So binary, what is binary? Now ask someone that question, ask someone what is binary, a lot of the time they're going to turn around and say, you know, it's some funky code that computers use and it's made of ones and zeros. Well, that's kind of true, but what really is it? What really is binary? Binary is what we call a base 2 counting system. Each bit being short for binary digit, can have one or two values. It could be a 1 or it can be a 0. Each bit represents a power of 2, and most of us know 8 bits form 1 byte. But what is it? How do we go about reading binary? What do all those little ones and zeros really mean? Well, to understand binary, we need to first have a little think about and understand how our everyday counting system works, how decimal works, or base 10. Now, in decimal, each digit can have one of 10 values. It can be a 0, a 1, a 2, a 3, a 4, a 5, a 6, a 7, 8, or a 9. And that's great for representing numbers between 0 and 9. But what happens when we need to represent a number bigger than 9? We need a 10, 11, a 12. We haven't got symbols for 10, 11, and 12, so what do? Well, we just simply add another digit to the left. So that means that every digit is going to be worth 10 times the digit to its right. That little table there just shows us the value or what each digit represents. So we can say over on the right-hand side in the least significant digit position, that's going to represent the ones. The next digit represents the tens, the next digit the hundreds, then the thousands, the 10,000s, and so on. So let's just think about the number 3,578. Think about how that's represented. Have a little look at the position of each of those digits. The first digit, over in the least significant digit position, the 8, that's going to be worth 1. Well, that's in the ones position, so we know that is going to be worth 8 times 1. The next digit, the 7, that's sitting in the tens position, so we know that's going to be worth 7 times 10. The next digit, the 5, in the hundreds position, it's going to be worth 5 times 100. And finally, our last digit, the 3, over there in 1000's position, is going to be 3 times 1000. So to understand the value of that number, all we have to do is add together the value of each of those individual digits. In this case, 8 plus 70 plus 500 plus 3000 gives us 3,578. Now this is basic stuff. We all know this stuff. We learnt this when we were 5 years old back in primary school. So how does this help us with binary? Well, binary works in a very, very similar way to our base 10 counting system. Instead of 10 possible digit values, binary is going to give us 2. It gives us a 1 and it gives us a 0. So this means that each bit is going to be worth 2 times the bit to its right. So that little table there will show us the position of each bit and its value. So we can see over there on the right hand side, the position of the least significant bit, that is going to be worth 1. The next bit, that is worth double the bit to its right. 2 times 1 is going to be 2. The next bit, the third bit, again, double the value of its bit to its right, is going to be worth 4. Then with 8, 16, 32, 64, 128, and so on. So let's take a look at the byte 11010010 and think about how we're going to working out what number that byte represents. The first thing we're going to need to do is just look at the position of each bit. Now, in binary, as with most counting systems, the zeros are worth nothing, so we can kind of ignore those. The only things we're really interested in are the ones, or more specifically, the position of those ones. Now, we can see the first bit we come to, working from the right-hand side, the first number 1 we come to is in the 2's position. So we know that bit is going to be worth 1 times 2, or straight up 2. The next bit we've got, the next 1, is sitting in the 16's position. So that is going to be worth 1 times 16. The next one in the 64's position is going to be worth 1 times 64. And the last one we've got over there on the left-hand side in the 128's position is going to be worth 128. So to work out the value of the byte 11010010, all we need to do is add together the value of each of those individual bits. So in this case, 2 plus 16 plus 64 plus 128 is going to give us 210. And that is binary. Binary really is that simple. And then before I go on, I just want to show you a little cool little thing that not everyone knows about. And that's the old Windows calculator. Now the Windows calculator has got a few different modes. We've got standard mode, we've got scientific mode, and we've got a programmer mode. In that programmer mode, we can select hexadecimal, decimal, octal, or binary. If we select decimal and just pop in a number, 210, our Windows calculator will give us the value of 210 in hexadecimal, in octal, and in binary. We can do the same with binary. If we just clear that and bash in some binary number, we can see the value of that binary number in hexadecimal, decimal, and octal. So it's just quite a cool little tool if you need to convert back and forth between binary and decimal. So with binary nailed, we can look at bitwise logic. So what is bitwise logic and how does it differ from Boolean logic? Now we're all familiar with Boolean logic. We use it every single day. We use it on our where clauses, our if statements, our case statements. Basically Boolean logic acts on 2 Boolean values. So if we take a look at that example where clause, where customer location equals England and purchases greater than 20, we can see there we have 2 Boolean values. Customer location equals England is going to be true or false. It's going to be a Boolean value. Purchase greater than 20 is going to be a Boolean value. It's going to be true or false. So those 2 Boolean values, we're applying the Boolean operator AND. That AND, as we all know, is going to look at those 2 Boolean values. It's going to evaluate them, and it's going to give us back a single resultant Boolean value. A Boolean logic gives us 3 operators. Strictly speaking, it gives us 4. There is not as well, but for today's purposes today, we're going to ignore not. Okay, we're not interested in not. We're only interested in ANDs, ORs, and XORs, or the exclusive OR. Now, I did have a little demo showing you Boolean logic, but I'm going to assume that everyone knows how Boolean logic works, so I'm just going to skip straight through that and get onto bitwise logic. Now, bitwise logic has very, very similar operators to Boolean logic. In bitwise logic, we have a bitwise AND, which in T-SQL is represented using the ampersand. We have a bitwise OR, the pipe, and we have a bitwise XOR, the caret. So bitwise logic works on individual bits of a value. So I'm just going to skip over to SQL and I'm going to show you bitwise logic in action. Just log into my machine, and so let's just zoom this in so you can see it a little bit better. So to apply bitwise logic in SQL, we can do something like this. We can say our bit value, our bitwise operator, in this case an AND, and our second bit value. So to run this select statement, all we're going to do here, we're just going to build up a bit of a truth table really for the bitwise AND. We're going to look at a bitwise AND applied to a 1 and a 1, a bitwise AND applied to a 1 and a 0, and a bitwise AND applied to a 0 and a 0. If we run that, we can see that this works in a very, very similar way to our Boolean AND, where both bits are a 1 or true, we're going to get back a 1. Where one bit or the other is a 0, we're going to get back a 0, and if both bits are 0, we're going to get back a 0. So that's a bitwise AND. What about a bitwise OR? Well, let's do the same thing. Let's build up this truth table. If we do that again, we can see this works in exactly the same way as our Boolean OR. So where both bits are a 1, we're going to get back a 1. Where one or the other is a 1, we're going to get back a 1. And where both are 0, obviously, we're going to get back a 0. And finally, the XOR, the exclusive OR. Okay, and you're not going to be surprised to learn that once again, the bitwise exclusive OR works in exactly the same way as the Boolean XOR. So remember, with a bitwise XOR, we're only going to get a 1 back where one value or the other value is 1, but not both. Okay, with an exclusive OR, the two bits, the two values are mutually exclusive. So that is bitwise logic working on individual bits. What about if you want to apply bitwise logic to something bigger, maybe a byte? Well, we can do something like this. We're going to say apply a bitwise AND to 220 and 177. What's that going to give us back? What result we're going to get back from this? Well, let's find out. SQL has given us back 144. And where's it got that from? How has it figured out 144 from 220 and 177? Well, to see what it's doing, we need to look at each of those numbers in their binary form. So 220 in binary is 110, 11, 100. 177 in binary is 10, 11, 00, 01. So how do we go about applying a bitwise AND to those two bytes? Well, remember what I said earlier on. Bitwise logic works on the individual bits of the values. So we're going to have to work through this bit by bit by bit. We're going to start over on the right-hand side. We're going to start with the most significant bit. We're going to apply a bitwise AND to the most significant bit of 220 and the most significant bit, its corresponding bit, in 177. Do that, we can see the most significant bit of 220 is a 1. The most significant bit of a 177 is also 1. We know that if we apply a bitwise AND to 1 and a 1, we're going to get back 1. Once we've got that, we can just move on to the second bit, the 1 in 220. Its corresponding bit in 177 is a 0. Bitwise AND 1 and 0 is going to give us a 0. The third bit, a 0 and a 1, will give us a 0. The fourth bit, a 1 and a 1, is going to give us a 1. The fifth bit, a 1 and a 0. The sixth bit, a 1 and a 0. The seventh bit, a 0 and a 0. So remember, a 0 and a 0 bitwise will still give us a 0. And last but not least, the least significant bit in 220 is 0. A 1 in 177 will give us a 0. So applying a bitwise AND to 1101, 1100 and 1011, 0001 results in the byte 1001, 0000 or 144. And that's bitwise logic. That is how bitwise logic works. Again, let me just show you something I quite like with the old Windows calculator again. So let's clear this out. Now the Windows calculator can perform bitwise logic for us. Up top here, we've got a few buttons here, one for each of the bitwise operators. So let's just try popping in 220 and 177, hit equals, and out pops 144. So again, it's just quite a neat little tool if you happen to be working at this level with bitwise logic or converting decimal into binary and so on. It's quite a neat little tool to have. So now that we've got bitwise logic nailed, we can move on to our first cipher. Our first cipher is the XOR cipher. Now the XOR cipher is used in many, many much more complicated algorithms. It's using AES, it's using DES, it's using all the derivatives of DES. To encrypt using the XOR cipher, all we have to do is apply a bitwise XOR against some key of some description and our plain text, our unencrypted data. To decrypt, we simply reverse the process. We will apply an XOR to our ciphertext, our encrypted data, and our key, the same key that was used to encrypt that ciphertext. So to hop over to SQL, we'll have a little look at that in action. So the first thing, hang on, I've jumped ahead of myself. Let's go back to my thing because I have jumped ahead of myself. Okay, so let's just look at how we're going to perform this before we jump into SQL. So for example, we want to encrypt the plaintext GroupBy. Now in SQL, T-SQL can only apply bitwise logic to certain data types. We can apply it to a bit, an int, a small int, a tiny int, or a big int. We can also apply to binaries and var binaries, but there is a slight caveat with this. We can't apply bitwise logic to a binary and a binary. If we want to use a binary, we have to apply bitwise logic to a binary and either an integer of some description, may it be int, small int, tiny int, big int, or a bit. Okay, I don't know why this is. I don't know why we can't apply bitwise logic to a binary and binary. There might be a very good reason within SQL for that. I have no idea why that is. If anyone that's more clever than me on Slack knows that, then feel free to let us know. We also, in T-SQL, cannot apply bitwise logic to textual data, to characters. Some languages will let us do that, T-SQL won't. And this is a slight problem for us because we want to encrypt the plaintext GroupBy. That's textual data. How are we going to be able to do that? Well, one thing we're going to need to do then is somehow convert that textual data into numeric data. How can we do this? Well, one way we can do it is to use the ASCII code of each character. So the ASCII code will give us a bunch of tiny ints, one tiny int for each character of our plain text. With that, we can then just apply an XOR, an 8-bit XOR to each byte of our plain text, each of those ASCII codes. That will give us some encrypted ASCII code, which we can convert back into its character representation, and that will reveal our ciphertext, our encrypted data. So now I can jump over to SQL and I can show you this in action. So the first thing we need to do is somehow get the ASCII code for the first character of our plain text, the G. Now SQL gives us this really beautiful little function, ASCII. Now ASCII will take in a character and it will spit out for us that character's ASCII code. So let's just have a little look at that. If we run that, we can see the ASCII code for an uppercase G is 71. You can check that against your ASCII tables. You'll find that is absolutely bang on the money. So now that we know that, now that we've got our ASCII code, all we need to do is apply an XOR to that ASCII code and some key value. This key value can be any 8-bit number. We've just chosen 1, 2, 3 here just because that's what I've decided to choose. If we do that, if we encrypt G using the key 1, 2, 3, it encrypts as an angle bracket. Now obviously if we change the key, we will find that our encrypted character will also change. That's great. That is really great. But how do we go about decrypting this? Well, to decrypt, we just do the reverse. We will apply our key, the key that was originally used to encrypt the data, to our encrypted ciphertext, do that, and out will pop G. Obviously, if we don't have the right key, we're not going to get back the right cipher, right plain text. So we can put all that together into a little routine, a little proc. Okay, so we're going to create a proc. Now, once I've done this, I'm going to stick all of this demo scripts, the slides are going to go up onto my GitHub site, so you can download these and play with them as you like. They're not there at the moment, but this afternoon at some point I'll do that. So we're going to create a little proc here. We're going to call it encrypt data XOR. Now, let's just change my database because I don't want to put this in my master database. So this proc is just going to loop through every single character in our plain text and apply our key using the XOR algorithm. So let's just create this proc. In it goes. And so to encrypt the data, the plain text GroupBy, we're going to just plug that into our proc. We're going to plug in the key 23 and out will come some encrypted ciphertext. To decrypt, we just do the reverse. We plug in our ciphertext, we plug in the key that was used to encrypt that ciphertext, run the proc, and out will come our now decrypted plain text. Obviously, if we have the wrong key, we don't have the right key, we're going to get back a load of old gobbledygook. So we've done it. So that is how we can now securely encrypt all of our data. We do that, we now know that next time someone hacks us, our data is safe. Well, someone has hacked us. Some dirty little thief has come in to our system. They've taken away all of our top secret sensitive data. But we don't care, do we? We're not worried about that because we know it's encrypted. We know there's no way that they can read that. Well, I hate to burst your bubble here, but they have. Somehow they've managed to decode all that data. They've managed to crack our cipher. How have they managed to do this? Well, our cipher, our XOR cipher, has got one very, very big weakness. Just have a think for a minute what that weakness may be. That weakness is its key, or more specifically, the length of its key. We used a single byte 8-bit key. Now, a single byte 8-bit key has only got 256 possible key values. That leaves it very, very vulnerable to what is known as a brute force attack. With a brute force attack, all the attacker does is simply try every single possible key value until they find one that works. It's about as subtle as David Banner in a bad mood, but it works quite nicely and well against weaker algorithms. So let's have a little look at a brute force attack. So we're going to run this little section of code. Now, this section of code, we're going to pass in our encrypted ciphertext, and we're just going to spin through, we're going to loop through every single possible key value. And remember, because we use an 8-bit key, we know the maximum key value we're going to have is 255, the biggest number that you can have in an 8-bit byte. So if we run that, we get back a load of possible plain text values. All we have to do now is just scroll through those plain text values until we find something that makes sense. And there it is. There is our original cipher, our original plain text now decrypted for the world to see. And we also now know the key. And this is a critical thing. We know the key that data was encrypted with. So any other data we have encrypted using the key of 23 is now compromised. So that is what my junior DBA would call a copious conundrum. How do we go about protecting against a brute force attack? Well, there's a couple of things that we can do here. We could make a longer key, or we could try and increase the complexity of our algorithm. Very, very few modern algorithms rely on a single round of encryption. The more rounds of encryption we use, the more complex our algorithm is going to become, and the more difficult it's going to be to crack. So before we think about any more, I just want to have a look at another cipher. I want to have a look at the Caesar cipher. Now, the Caesar cipher was allegedly invented by the Roman Emperor Julius Caesar. He was a clever guy. To encrypt using the Caesar cipher, all we do is just shift each character of our plain text by a set number of characters in the alphabet. So, for example, if we want to encrypt SQL Undercover, we could just shift each character in our alphabet by 2. That would give us the ciphertext USNW PFG TEQXGT. So just to see how we got to that, let's take a look at the position of S in the alphabet. We shift by 2. That'll give us a U. So how can we go about implementing the Caesar cipher in T-SQL? Well, it's very, very simple. All we need to do is add a numeric key to a character's ASCII code. Simple. With 256 possible ASCII codes, that gives us 256 possible shift positions. Hang on a minute. With 256 possible shift positions, this is no more secure than our XOR cipher was. It's going to be just as vulnerable to brute force attack. This is not going to be good enough. I'm sorry, Julius. I'm sure 2,000 years ago, this was fantastic. This was great for passing encrypted orders to your armies, but today it is just not going to cut it. But what about if we were to combine the XOR and the Caesar ciphers? We could then perform maybe an XOR cipher followed by a character shift. Our cipher will suddenly become much more complicated, much more complex, and much more difficult to crack. So the XOR cipher has 256 possible key values. It's weak. We know it's easy to break. We can brute force that, no worries. The Caesar cipher, 256 possible shift positions. That's no better than our XOR cipher. But just think about those numbers. 256 possible key values. 256 possible shift positions. If we were to combine those two ciphers, that would give us 65,536 possible shift key combinations. So by combining these two relatively weak ciphers, we can make something much, much stronger. Now, okay, I'll admit to you, 65,000 odd shift key combinations in a world of modern computing is not going to be difficult to crack. It's going to be fairly easy to brute force. But for the sake of this demo today, I'm not going to sit here scrolling through that many possible plain text values. So we're going to say that 65,536 possible shift key combinations is good enough. That is going to be resistant to a brute force attack. So let's just hop over to SQL and we'll have a little look at this in action. So the first thing we need to do is get our ASCII code and perform a shift on the ASCII code. Essentially move the G 2 places along in the alphabet. If we do that, we end up with an I. So A, B, C, D, E, F, G, H, I. To decrypt the Caesar cipher, we just reverse it. We'll do a reverse shift on our ciphertext. We do that, and out pops the G. So how do we combine the Caesar cipher and the XOR cipher? Well, quite simple. We'll first perform a Caesar cipher. That will give us some encrypted ASCII code. We'll then apply a bitwise AND to that, a bitwise XOR, to that with some key value. Doing that on a G will give us the character 2. Now, obviously, if we change the shift, our ciphertext will change. If we change the key, our ciphertext will change. So to decrypt, we just turn the whole thing on its head. We grab the ASCII code of our ciphertext. We apply our XOR encryption to that. We then do a reverse shift. Doing that on a character 2 gets us back to our original plain text. Again, we can pop that into a little proc. This time, we're going to pass in our plain text as before. We're going to pass in our key as before. We're also now going to pass in a shift position. And because the encryption and decryption algorithms are slightly different, we can pass in a decrypt flag. So this is going to tell us whether it's encrypting or decrypting, so which algorithm we're going to be using. So let me just run that in. So as you can see, exactly the same as before. We're just going to loop through each character in our plain text. We'll apply the relevant algorithm to that, which will build up our ciphertext. So let's just run that in and try encrypting the data GroupBy using the key of 210, the shift of 2, and because we're encrypting, the decrypt switch is switched to 0, which will give us some ciphertext back. To decrypt, we just do it the other way around. We pass in our ciphertext. We use the same key that was used to encrypt, the same shift value that was used to encrypt. But this time, because we're decrypting, we switch the decrypt switch to 1, and out pops our decrypted plain text. Now, obviously, once again, if we don't have the correct key, we're not going to get back the correct values. And the same is true of the shift. So now we have it. There we have it. We can now securely encrypt all of our data so that it is now resistant to a brute force attack. So now, next time, our dirty little thief comes in, steals all of our data and goes running off with it, we can laugh at him. We can laugh and we can point at him because we know he can't read any of our data. Well, he has hacked us again. He has got our data and he has somehow once again managed to decode our ciphertext. He has cracked our cipher yet again. How has he managed to do it this time? Well, the XOR Caesar cipher has got one big weakness. What is that weakness? Have a little think what that may be. It's a straight substitution cipher. Now what that means is that every unencrypted character's encrypted counterpart will always be the same. So if we hop over to SQL, I'll show you what that means. Let's try encrypting the text AAA, BBB, CCC using the key 113, the shift of 2. If we do that, we can see that A always encrypts as 2, B always encrypts as 5, C always encrypts as 4. Let's just pop A, B, C onto the end of that. Let's run that again. And again, we can still see A is 2, B is 5, C is 4. That is a problem for us. It is a problem because it means if we can work out what an encrypted character represents, we'll know all the occurrences of that character in our ciphertext. Substitution ciphers are very, very vulnerable to what is known as statistical attacks. Statistical attacks, also known as statistical analysis or frequency analysis, work on the fact that certain letters and combinations of letters in the English language occur more often than others. So by analysing the ciphertext, we've got a pretty good chance of being able to identify these common patterns. That little table there shows us the most frequently occurring characters in the English language. So we can see that E shows up around about 12.02% of the time. A T shows up a little over 9% of the time. An A, 8.12% of the time. And again, down at the bottom end of the scale, we can see a Z. A Z is only going to rock up around about 0.07% of the time. A J, 0.1% of the time. So we can use these sorts of numbers, these sorts of statistics to guess, to try and predict what each character in our ciphertext represents. So let me again just pop over to SQL and I'll show you this in action. So first of all, we're going to try and encrypt this nice chunk of data here, this nice chunk of text. Now this is just something I've grabbed off the BBC News website the other day. So if we encrypt this, we get back a nice big chunk of fairly unintelligible ciphertext. How do we now go about analysing this? How do we go about breaking this down? Well, the first thing we need to do is analyse the frequency of each character, count up how often each character appears in that ciphertext. So we've got a little bit of code that will do that for us. First of all, we're going to create a temp table character frequency to hold these frequencies for us. Let me run that. And then we're going to run a little bit of code now which is going to populate that for us. This is going to go through each character of our ciphertext, a ciphertext which I've plugged in here, and it is going to count up how often each character appears. So let's just do that now. And just select from our character frequency table just to see what we've got. So straight away we can see that certain characters are showing up more often than others. Just to make things a little bit easier, we're going to fill out that frequency rank row. Okay, I'm not going to go through all the code and how it all works because I say it's all up on GitHub. So if you do want to have a poke around, play around with it afterwards, jump up there, grab it down, and you're free to do so. So now if we select from our character frequency table now, we can clearly see what the most commonly occurring characters are, and those that show up not very often. Knowing this, we can now start analysing the character. We can start making assumptions and guesses on what each of those characters is going to represent. Now, one thing we do know is that the most commonly occurring character in a big old chunk of text like that is always going to be the space. And you can see, sitting up here, number 1, the open bracket, which shows up 267 times, almost double the amount of times our next most frequency character appears. So we can make a pretty good guess then that that open bracket represents a space. Now, a lot of algorithms actually either get rid of spaces or pad them out or do something with them just to stop this. But just for today's demo, I haven't done that. So knowing the space, we can now just update our frequency table. So we can now see that our first character, the open bracket, predicted character is now, that is a space. And for now, it's very, very simple for us now just to take our original ciphertext and just replace each occurrence of that space, of that open bracket in our case, with a space. If we do that, it then suddenly makes it very, very easy for us to be able to recognize and be able to identify individual words in our ciphertext. Knowing individual words lets us now perform a bit more analysis. We can start looking for common patterns. One thing we all know is that the most commonly occurring single character letter in the English language is going to be an A. So all we need to do now that we know spaces, we can have a little look through, we can count up every occurrence of a singly occurring letter, which we'll do this little bit code here. We run that. We now select from our character frequency chart. Down at the bottom, we will see each occurrence of a singly occurring character. So this time, we've only actually got one character here that shows up on its own, and that is an I. That shows up 7 times. So we can be pretty confident that I represents an A. So again, let's just update our character frequency table with that. We'll just clean it up, so we'll just remove all those little patterns we last put in. And now select from the character frequency table, and we can see that we predict that is going to represent an A in our ciphertext. And we can carry on. I mean, the demo here goes on a lot further. I'm not going to go through the whole demo because it takes time, but we can carry on now. We can look at, there's other patterns we can look for. We know the most commonly occurring 3-letter word is the. So we can analyze all the 3-letter words, find the most commonly occurring one, and we've now identified a T, an H, and an E. We also know the most commonly occurring 3-letter word that begins with an A is an AND. Well, we know what A is, so it shouldn't be too difficult for us to find an AND. Do that, and we've got an N and a D. So this is just the way that these sort of statistical analysis can be done. As I say, I'm not going to go through the whole script. You can grab it off GitHub later on and play around if you like. Again, and try using different plain text and see how it gets on. So how do we now go about against producing something that is resilient to a statistical analysis? Well, to avoid being vulnerable to statistical analysis, we need to make sure that a character isn't going to be always encrypted in the same way. Look what happens when we try and encrypt the string AAAA, as we have been doing using an 8-bit key. We start off with our plain text. Every byte is the same. We're encrypting identical characters. Because we're using an 8-bit key, that means that our 8-bit key is applied. The same key is going to be applied to the same character each time. That means that every single character is always going to be encrypted in the same way. How can we get around this? How can we prevent this from happening? Well, what happens if we try and encrypt data using a 32-bit key, for example? We'll start out again with the same plain text, the same 4 identical characters. But this time, because we're using a 32-bit key, we can encrypt a different portion, a different byte of our key against each byte of our plain text. And that means that every character, even if they all started out the same, is going to be encrypted differently. This makes it far, far more difficult to carry out a statistical attack. But how does this do against a brute force attack? Well, using a 32-bit key that gives us just over 3 million possible key values. So I'm going to say that's doing pretty well. So again, let's just jump over to SQL and see about how we can build this up. Let's get to the bottom of that demo. So again, we're going to create a little procedure. This time we're going to call our procedure encrypt data, the pimped XOR. We're going to pass in a key. Now this time, we're going to use a big int. We're using a big int because before we used a tiny int, now we're using a much bigger number. We're using a 32-bit number, so we're going to need a big int to hold that number. We're going to pass in our plain text. Now, instead of looping through every character individually, we're going to break our plain text down into 4-byte blocks. We're then going to just apply our key, our 4-byte key, against that 4-byte block. And that will build up our ciphertext. So let's just run this in. And now let's see this in action. So if we attempt to encrypt the string AAAA using our now much longer key, before those A's would have all encrypted to the same character. Now, with our new pimped XOR cipher, our new longer key, we can see, let me just scroll that up, we can see that each character, each occurrence of that A encrypts differently. To decrypt, we're just going to plug in our ciphertext. We're going to use the same key that we used to encrypt, and out will pop our now decrypted plain text. So there we have it. We've done it. Now we have done it. Now we know we can produce a cipher that is resistant to brute force attacks, that is resistant to statistical analysis. So now, as he has done it again, that dirty little data thief has come in, stolen all our data. He's going to run off with it again. We know, we can laugh, we can point at him because we know he can't read that. He can't decrypt that using the methods he's done before. Well, we have another problem. Once again, this devious little fiend has managed to decode our ciphertext. He's read all of our data. He has cracked our cipher. How? How has he managed to do it this time? Well, let me tell you something about called a plain text attack. In a plain text attack, the idea is that by analyzing the ciphertext and even just part of the plain text, we can reveal a whole or part of the key that was used to encrypt it. XOR ciphers, regardless of the key length, are very, very susceptible to plain text attacks. Let me show you why that is. Let's start at the plain text 10111001. We'll apply the key 10101010 to that. That gives us the ciphertext 0001011. Now look what happens if we try and XOR the plain text and the ciphertext. We have our plain text, we have our ciphertext. Now XOR those together and we get the result 10101010. We're back, we've got our key value out. And that is a massive, massive problem. So if we can somehow discover a portion of the plain text, we can use that to retrieve the key and crack the rest of the message. Now, there's a few ways we could get hold of that plain text, that portion of plain text. We may have performed some sort of statistical analysis already, which has revealed part of the text that we can use. Perhaps we've managed to intercept part of the original plain text, or we may have just guessed. Now, guessing isn't as silly as it sounds either. Imagine some sort of things we encrypt. Perhaps we're encrypting a name, okay, a first name. Well, there are only so many common first names out there, so we can have a pretty good go at guessing what that first name could be. Just to say, yeah. So look at the following. The following was encrypted using a 16-bit key. Somehow we have managed to get the first 2 bytes of the plain text. All we now need to do is XOR those 2 bytes of the plain text against the ciphertext. We'll have the key. We can easily decrypt the rest of that ciphertext. We don't even really need to reveal the whole key. Just a single byte in that key is going to allow us to decrypt half the characters in the message. If we can do that, we seriously weaken the cipher. You know, it was a 16-bit key. There's only 8 bits left. We could probably perform a brute force attack on that. We might be able to do some other sorts of attacks. So just hop over to SQL and I'll show you a plain text attack happening. So we're going to create a little proc. We're going to call that the Crackomatic. Into that proc, we're going to pass some plain text. We're going to pass our plain text and our ciphertext. We're going to build up a 4-byte ASCII representation of each of those plain text and ciphertext and just apply an XOR against the two 4-byte blocks. So let's run this in. And now look what happens when we try and encrypt the data GroupBy using the key value 4027558485. We get back some ciphertext as we'd expect. Now our attacker has managed to somehow get hold of the first 4 characters of our plaintext. He plugs that into the Crackomatic along with its corresponding characters, its corresponding bytes from the ciphertext. Do that, we get back the value 4027558485. We've got back our original key. And that is a massive, massive problem because we can now use that key to decrypt the rest of that data. And also, obviously, we now have the key value that was used, so any other data that was encrypted using that key value is now compromised. That, in the words of my junior DBA, is a copious conundrum. So, how do we go about protecting against that? Well, we need to go back to a little bit more binary. We need to look at a bit shift. So what is a bit shift? A bit shift is kind of like what it sounds. We simply shift the bits of a byte either left or right by a specified number of positions. So if we were to perform a left bit shift on the byte 10000001, let's see what happens. Well, the first thing that happens is the most significant bit is dropped off. We get rid of that. That's gone. We then shift every single bit along by 1, and then the least significant bit we pad out with a 0. That's a bit shift. Circular bit shift is slightly different. What is a circular bit shift? Well, it's similar to a standard bit shift, except that instead of throwing away that most significant bit, we move it to the position of the least significant bit. So again, let's see this happening. First of all, let's move that most significant bit aside. We shift our byte by 1 bit, and instead now of padding our least significant bit with a 0, we take whatever that most significant bit was, in this case it was a 1, we move it into the position of the least significant bit. So that most significant bit always cycles around. How can we perform this in T-SQL? Well, unlike some languages, T-SQL does not provide us with a bit shift operator. So we're going to have to do it some other way. Let's just have a little look at what happens when we perform a left bit shift on the value 1. Left bit shift will provide us with 2. Let's do a left bit shift on the value 2. We get a 4. Do you notice the pattern here? Every time we perform a left bit shift, the value is doubling. So we can kind of cheat a little bit really. In T-SQL, all we need to do is by multiplying that value by 2, we'll have the same effect as a left bit shift. We've effectively shifted all the bits to the left by 1. What about an overflow? Well, remember what I said. With a bit shift, the most significant bit is usually dropped off. That's got shot off. If we try doing this in SQL, it's going to cause us an issue. Either SQL is going to exceed the maximum value of the data type we're using and chuck us out an error, or the value is going to simply exceed what we're expecting it to be. So what can we do? How can we check for a overflow? Well, first thing we need to do is check the value of the most significant bit. We can use this funky little bitwise logic to do that if we want to, using a bitwise AND, or much simply, we can just check if the value of our number is equal or greater than that of the most significant bit. If that's true, then we know that most significant bit is going to be a 1. If we detect an overflow, we just subtract the value of the most significant bit from the value, and then we shift. So a circular bit shift in T-SQL. What are we going to do there? It's very, very simple. we're going to first check for an overflow, as we've already done. If we detect an overflow, we'll deal with it the same way described earlier. We'll shift the bits, and then we simply add a 1 to our number. So adding a 1 just simply will effectively change that least significant bit to a 1. If we do not detect an overflow, if we decide that most significant bit was a 0, we just don't need to worry about it. So how can we now make an algorithm that's resilient to a plain text attack? Well, let's just look at the following example. We start with the plain text 011000101. We'll apply the key 11110000. That will give us the ciphertext 10010101. Now we know if we XOR that ciphertext with that plain text, we're going to get back our original key. But what if we were to perform a second round of XOR? What if we were to shift that, perform a cyclic bit shift on that key and use that bit shifted key to perform another round of XOR against our ciphertext? Well, shift that key by 1, we end up with the key 111000001. Apply that to our ciphertext, and we get the final ciphertext of 01110100. Let's have a look at that, the plain text and the ciphertext. Apply an XOR to those two, and we get 00010001. Now that does not match our key. So, and this is exactly how algorithms such as DES works. DES does it, there's a bit more jiggery-pokery with DES, but essentially what DES does is that it will perform 16 rounds of an XOR cipher. Each round is performed using a bit-shifted key. So the key will either shift 1 or 2 bits, depending on what round of XOR it's on, and out will pop at the end some ciphertext. This makes things much, much more difficult to perform a plain text attack against. So let's just hop into SQL, and I can show you that in action here. So again, we're going to pass into our new algorithm. Actually, I've called this mini-DES. Originally, I had the algorithm called mini-DES before I changed it on the slide. So the demo script's a little bit out of date. But we're going to pass in our big int key. We're going to pass in our plain text. Now, the first thing we now need to do is produce 2 keys. Now, the first key, which will be used in the first round of the XOR, is simply going to be the key that we pass in. The second key, we are going to just perform a bit shift against. We then just loop through each 4-byte block from our plain text as we did before. First of all, we apply a first round of XOR. So that will be using our original key. We then, against the encrypted data we get back from that, will perform a second round of XOR using our bit shifted key to give us our final ciphertext. So let's just create this proc. Let's just try encrypting some data. So we're going to encrypt the data groups by using the key 4027558485. And we can just decrypt these in the same way, passing in our ciphertext and the key that was used to encrypt that ciphertext, and out will pop our original data, our original plain text GroupBy. But what about if we want to perform a plain text attack at this? Let's try. Once again, our attacker has managed to get hold of the first 4 characters of our plain text. So he is then going to plug that now into the Crack-O-Matic along with its corresponding characters, its corresponding bytes from the ciphertext. If he does that, now we get back the value 269549310. That does not match our original key value. And if we try and encrypt that ciphertext using the key we've just got back from our Crack-O-Matic, we'll see we get back a load of old gobbledygook. So by doing that, by shifting the key, we can now build something that is resistant to the plain text attack. So that pretty much brings me to the end of this session. But there is one final question. SQL Server gives us some really, really great ways to encrypt our data. We've got all sorts of brilliant ways of encrypting data. So what is the point of hand cranking our own routines? Well, that is a good question, and was kind of the point of today's session. First of all, I hope it's been quite interesting to see how encryption works inside and how the cogs turn. But also, I want to try and make a point that DIY encryption is pretty easy to crack unless you really know what you're doing. All we've looked at is some very, very basic, very fundamental attack vectors. There's much, much more clever guys out there than me that can do much, much more clever stuff or much, much more complicated algorithms. So if you do decide to hand crank your own routines, think about it. Be very, very careful. Just bear in mind that DES with its 52-bit key and its 16 rounds of XOR is now considered insecure. So that pretty much brings me to the end of the session. So thank you very, very much for listening. I hope you did find it useful. And that's me. Thank you.
Nice job, David. Very cool. And of course, as we're saying in Slack, everybody's pretty much now terrified and glad that they don't have to write anything for encryption.